Welcome back to CEDAD's seminars. Today's seminar is about semiconductor detectors, in particular pixel detectors. The development of microsegmented semiconductor detectors have represented an important technological step forward in many research fields, including nuclear physics. Probably without the developments of such detectors, important discoveries such as the Higgs boson would not have been possible. Our guest today is Enrico Junior SCHIOPPA. He will review the working principles behind these intelligent pixels and give an overview of their potentialities in different fields. These devices keep being an essential element of modern detectors at collider experiments, as an ever-increasing degree of intelligence is being stored in each single pixel. This feature also provides for incredible versatility to such an extent to the very same detectors keep finding applications in growing number of fields outside of fundamental physics. Enrico Junior SCHIOPPA got his degree in nuclear subnuclear physics at the University La Sapienza in Rome in 2010 with honors. He then enrolled in the PhD program of the Dutch National Institute for Subatomic Physics at the NICEF laboratories at the University of Amsterdam, where he worked on potential applications of novel pixel detectors in X-ray computer tomography. He was awarded the Young Cliver Prize. He then moved to the University of Geneva in Switzerland, where he worked on the realization of UV camera prototype of the small-size telescope of the Cherenkov telescope array built with silicon photomultipliers. From 2016 to 2019, he was at the CERN Fellow in Applied Physics, where he worked on the development of novel radiation-hard monolithic pixel detectors based on CMOS technologies. Since then, he is also part of the Atlas and RD52 collaborations. He came back to Italy as an RTDA researcher with a PON action for international mobility for researchers. At the University of Salento, in strong collaboration with the Lecce section of the INFN, is working on the realization of future in-depth tracker of the Atlas detector and is developing data analysis methods based on artificial intelligence. Since 2019, Enrico is also a scientific consultant of Dynaction, a Dutch startup located in the Eindhoven high-tech campus, which is developing novel security scanners based on fast neutron beams and artificial intelligence. He is author of tens of international publications and one patent. The title of the seminar is Intelligent Pixels.
Okay, thank you very much, Professor Calcagnile, and thanks to all the crew of this beautiful lab for organizing this. I will talk about, my experience in silicon detectors has been quite broad. I've been working, as a professor introduced, on pixel detectors in both hybrid and monolithic fashion, as we will see in this talk, and also on silicon photomultipliers. So what I found always interesting is the fact that these detectors, despite being developed mainly for applications in high energy physics, like discovering new particles or exotic new states of matter, can have a lot of potential for applications outside this field. So what I would like to focus on today is mostly this part, how this technology can be exported outside the high energy physics field. And I mean, the number of possibilities is huge. And what I will cover today is just the tip of a big iceberg. And of course, I chose these topics just because it's the ones where I have a bit more experience. Okay, so just to set the stage, to understand where we are as a framework, we're talking about semiconductor detectors. So the principles that we'll be using and that we have to keep in mind throughout the whole talk is just this. A particle crosses a piece of semiconductor, whatever it's going to be, silicon, germanium, something more exotic. It deposits energy, which is converted into electron holes. And these carriers will drift away from each other because there is usually, there must be a potential difference applied by some electrodes. Okay, and this motion of carriers in both directions is what induces a signal on the electrodes. Okay, and that's what we are going to measure. This is a general principle. If we want to make a pixel detector out of this, we take a piece of silicon like this. We put a back metallization which is uniform on the back, and on the other side we make many tiny metal implants or highly doped implants, and this becomes basically the pixel matrix. So that's how we make pixel detectors. So having said that, I think the rest will just follow. Okay, so first of all, what are we talking about when we talk about pixels? So if you look at the human hair in this picture, and you look at the size of the pixels that we will be talking about, or that are most commonly used around the world, we see here in this box we have the LHC detectors, which all use pixel detectors in the core, which is close to the interaction point. And this is the size of the pixels of the 4 detectors, Atlas, CMS, ALICE, and LHCb, compared in scale to the hair. Okay, so this is the sizes we are talking about. There are other pixel detectors that can do slightly better in size, if you want. A CCD or a CMOS camera, which is in your phone, would use a pixel which is the size of the dot, which is probably unperceivable for you. And the human retina, the pixel size is again a dot which is not perceivable for you. The difference between these pixels and these pixels, which are slightly larger, is the fact that these ones are larger not because we don't want to go smaller, but because inside of each pixel we want to implement a lot of intelligence. And that's what I will describe soon. Another thing that we have to keep in mind is that there are 2 flavors of these detectors, and it's just a technological aspect. Okay, We have the sensitive part, which is, again, this piece of semiconductor in which these charge carriers are going to induce a signal. And then, of course, you need electronics to see the signal and to process it and to turn it into something digital, maybe. And this can be done in two ways. Either you manufacture the sensor and the electronics separately, and then you join them using these so-called bump bonds, so these tiny microscopic spheres of conductor that just join the electrodes in the sensors with the input electrodes of the electronics. And here you see a nice SEM picture of this. Okay, in this case, one talks about hybrid pixel detectors. If you don't want to do this for a number of reasons, okay, this process is expensive. It doesn't have a very good yield, which means that okay, you might have produced the best sensor and readout, but then when you join them together, something goes wrong there, and you lose a lot of pixels just because you don't have connection. So it's kind of a risky process to do. So there are a number of reasons why you don't want to do this, and you want to do that. So you just process the same wafer to implement both the sensitive part and the readout in the same substrate. Okay, and one may think, okay, this sounds much easier than this, so why don't people just do this? Well, there are a number of reasons why. The first one is technological. So that one, the monolithic one, is technologically more challenging to do with respect to this. And maybe I will, you will have an idea of why in the next slides. Second is that this solution is actually more versatile. Okay, here you are stuck to silicon. You can do we can do electronics in silicon, and therefore, if you want to grow a sensor top, well, that's silicon as a substrate that you have. Here, the sensor can be anything. Can be silicon, can be cadmium telluride, can be a gas, can be something completely different. Okay, so here you have versatility to do a lot of stuff. Just to say just a few words about the second one, the monolithic one, and why it is so challenging. I show you just this thing here, which is what I worked on when I was at CERN for 3 years. So these are the two sub-flavors, if we want, of the monolithic design. So now we are looking at 1 pixel in a cross-section. Okay, so this would be the silicon substrate, which is, for example, p-doped. And then you want to do electronics on it. So you do a lot of p-n junctions and transistors that you place there, okay, to do all the electronics you want to do. And this you keep as your sensitive part. So the particle will go here. It will generate electron hole pairs. And this will be collected by this deep and well. So this is a highly doped N implant in the P substrate. So here you have a p-n junction, you have a field, and therefore you get the drift and the building up of the signal by induction. And then you transfer this signal to the electronics. Okay. Now, this is nice. Okay. However, all of this is the input electrode. Okay. Which is nice because it makes a nice uniform p-n junction, a nice field which is more or less the same everywhere, despite, okay, pending the fact that a field in a p-n junction is linear and not uniform, but okay, it's very homogeneous as a structure. Okay. The only problem is that a big electrode means a big capacitance, and a big capacitance means a lot of not nice things, let's say. Let's put it like that. First of all, a capacitance will enter in the definition of the tau of whatever the circuit is going to be there. So you have a tau equal RC for whatever R is for the resistive impedance of the circuit. So you have a slow circuit basically. Okay, that's one of the main drawbacks. So you might think, okay, let's try to shrink this electrode to bring down the capacitance and make a faster detector. Not only speed is affected. If you remember from physics, there exists a source of noise which is connected to capacitance, which is called the Johnson-Linguist noise, that tells us that whatever there is in the electronics, okay, you are going to have fluctuations in the signal simply because of thermal agitation here, which means that you have a fluctuation in the charge here, which is going to sum up to the charge that you actually create. So the signal to noise ratio is going to be large here because this charge is proportional to to the size of, to the capacitance, basically. So going down in capacitance also means increasing the signal to noise ratio on top of increasing the speed. When you do this, you can do this thing. So now your electrode is very tiny, okay? And then you can transfer the induced signal on all the electronics that you want. The problem here is that the junction, the p-n junction that makes your detector work, that makes your electric field, that makes the charges drift and induce a signal, well, that's confined in a small region around the electrode. You can increase the voltage, the bias voltage of the junction, but at some point, the risk of reaching breakdown before actually depleting all the useful volume is quite large. Okay, so you have to be really smart to make it in such a way that you can actually deplete all this stuff. One thing that we did to, let's say, to minimize this effect is that we changed a bit the process together with the foundry. And we, let's say, invented this kind of thing. We implanted a uniform N substrate in the P substrate, so that now we have two p-n junctions, the one which is at the pixel electrode, and the one which is uniform over the matrix. Now, when you apply the back bias, the reverse bias, now this junction grows, but also this junction grows until they meet, and now you have all a nice uniform depletion over all the volume, let's say. So you have a much higher sensitive volume and a more uniform matrix. Okay, so this is just a very, a very quick example of why, of what the challenges are from the point of view of technology in building these new types of detectors, the monolithic one. The nice thing of having a monolithic detector is that, okay, if this really works, and we prove that this works, and it even works up to radiation doses received by this thing, which are in the order of the ones that are expected for the lifetime of a high luminosity LHC, at least in the outer regions of the inner tracker. Okay, so quite high doses. The nice thing is that since your capacitance is small, you have a very high signal to noise ratio, so you can actually work with lower signals, which means you can make this detector thinner. Now the particle that crosses it will have less, a smaller distance to leave actually charge. So the total charge will be less than a particle that would cross a larger volume. But you don't care because it's still enough to counteract the effect of the noise and still be seen, despite it's so small. So you can make much thinner detectors, which are quite useful for high energy physics, because in the very core of our detectors, we want to be as light and thin as possible, because there we just want particles to cross the detectors almost unseen, just enough that we can reconstruct the trajectory, but not too much that we are, we are receiving all the effects of multiple scattering and disturbing the trajectory. So thin detector is also a nice thing there. Okay. So, and now about the electronics part. For this, I would like, maybe it's easier to explain if you just allow me to do a small sketch. Suppose that this one is okay. This one is your sensor, whatever. A particle crosses the sensor and generates electron holes, and then there is a potential difference here. So the movement of these charges is going to induce a signal on an electrode here. And now, from this pixel, you have to go to all the electronics, which is below it. Okay, what do you want to do? Okay, first of all, you would like to amplify it, most likely. So you would have an amplifier there with all the stuff that needs to be there for the case. So here you have a nice amplified and shaped signal. And this part here, which I drew as a magic box here, is actually quite important, because this is what shapes the signal. And we do it in such a way that the signal assumes a very specific shape, which is something very approximately that we can very well approximate as a triangle, whose area is proportional to the deposited charge. Okay, and also, yeah. This means that if now we have a way to measure, oops, this was not that nice, to measure this quantity, suppose that now we have a threshold, Okay, so we say that all the signals that are higher than this threshold are actually signals, and all the noise which is produced below here, we don't see it. Okay, so our pixels are now noise-free, and they just detect signals when an actual particle crosses it. Okay, and the signal is proportional to the charge that was deposited in this sensor. Now, since the area of this signal, we did it in such a way that this is proportional to the charge, it also means that the duration that the signal stays above threshold is itself proportional to the charge. So the TOT, the time over threshold, is proportional to the charge that was deposited in the sensor. This means that a pixel which has this kind of electronics inside is a pixel that not only detects single quanta, but it can also measure the energy somehow. And this way, I mean, this thing is achieved by adding a discriminator, which is the thing that applies the threshold. Okay, so here you would have a threshold. And then something somewhere, some digital circuit that does this job. So for example, you can have, as soon as the signal crosses the threshold, the discriminator is going to trigger a clock, for example. And this clock stops when the signal goes back below threshold. Okay? And by counting the clock cycles that happen during this interval, well, then you know you have a time, some delta t, which is proportional to the TOT, which is proportional to the charge. Okay, so this is one way we have to achieve spectroscopic capability in every single pixel for every single particle which is detected. Okay, imagine you had a photon. A photon would do photoelectric effect. Okay, it would release all its energy into a photoelectron that would travel for a very tiny distance at energies, for example, of the X-rays. So we are talking about kV, tens of kV, hundreds of kV. The photoelectron will basically be contained inside the very same pixel, which means that all the charge is produced near the place where the photon was actually absorbed. Therefore, this pixel sees all the charge which is proportional to the energy of the photon, and therefore the TOT, the time over threshold mu measure, is actually the energy of the photon, which is really interesting. We will see later why. Okay, so that's basically what I just explained. So you can have, if you want to draw it a bit more complicated, it's going to be like this, but it's basically what we just saw. And you can do this, yeah, this one is what I just explained. As soon as the signal goes above or below threshold, you just count. You can do something more sophisticated or less sophisticated. I mean, you can just count signals, okay, within a time window, so you are just counting photons or quanta. Or you can measure the time of arrival. You can start this clock as soon as a particle gives a signal that goes on top of the threshold, and then you don't stop it until you just reset something, which can be the trigger of your experiment. So you're basically measuring the time of arrival of the first quantum that enters this time window that you are considering. Okay, and this is also another feature that maybe I will explain how we can use it. Okay, fine. And this is how it would look like if you look at a real pixel matrix. This one is an example of a monolithic matrix. It's 512 times 512 pixels. It's roughly 4 centimeters square. And if you look at what the pixel looks like, it's a 36 times 36 micron square pixel. And you see, this is the tiny electrode. It's just a few microns square. So the capacitance is very, very tiny. So the signal to noise ratio is very high, and the speed is very high. It's isolated from the rest of the electronics, the one that does all the circuitry that we just saw. And you see it's divided between analog and digital. You need analog stuff to do all the amplification and shaping, and then you go into the digital realm and you do all the other stuff you want to do, counting clocks and all these kind of things. So this is what I call, or someone else also calls, an intelligent pixel, if you want. Okay, let's now jump into an example of an application where these things are being very useful outside high energy physics, okay, which is spectral computer tomography. This is something I worked on during my PhD, so from 2010 to 2014, and then I changed subject, so I didn't have time to follow it. I mean, I followed it, but I could not work more on that. But I like it because it's really a very nice example of what this can, of how this technology can be useful. Okay, so we're talking about X-ray imaging. So you have a beam of X-rays, and you create contrast in an object by, ideally by counting how many photons are absorbed with respect to how many photons cross the object, and this ratio is different depending on the density or the composition of the object you are imaging. So different materials will give you a different contrast on the other side. This is stuff we all know. And computer tomography in particular is a technique that allows us to do three-dimensional reconstruction in 3D in X-rays, because you basically do an image of the object at different angles, and then you reconstruct this image. Okay, to understand how this thing is going to be useful for us using this technology, I would like to do just explain very quickly what the problem is with computer tomography. How one can go from a set of images at different angles to a real 3D image. Well, it's quite easy, in fact. So if you take a beam of X-rays that contains, I don't know, n X-rays per second or whatever, this is going to be the flux, whatever this n is going to be, and then you have a material which is characterized by a density rho, whatever. Then at the other side you will see less X-rays. So this is going to be n0, this is going to be n. And if we call mu the linear attenuation coefficient of X-rays in this material, then we know that n over x, where x is the thickness, is n0 e minus x mu. Okay, so it just decays exponentially. Okay, so the thicker it is, the fewer photons. The fewer photons you see at the other side. Okay, so that's the basic setup, which is, however, a very crude approximation of what's really going on. First of all, we are assuming that this object here is uniform. Okay. In the most general case, rho is not a fixed number, it's not a scalar, it's going to be a rho over x. Okay, so at least we have to do n of x, n0, e minus, now instead of multiplying this mu, okay, which is as well dependent of x, now we're going to substitute this with an integral. Okay, so now the total attenuation is the summation of many small steps. Okay, and then the other thing which is really missing is that here we are assuming that this n0, this flux of photons, is monochromatic basically. So all the photons here have the same energy. Now, either you have an iron 55 source, or you are at a synchrotron. It's very difficult that you can get X-ray imaging with a monochromatic source. Typically, we use X-ray tubes, which emit a very broad spectrum. It's something like, it's the spectrum of X-ray tube is a Bremsstrahlung spectrum, so it's going to be something like this with some characteristic lines. So definitely something which is not monochromatic. And we also know then that then this n0 is not n0, but is some n0 dE, so it's a spectrum. And this is going to depend on energy. So this is going to be a mu of x e. Okay. So this means that the formula starts to get quite complicated. So it's going to be, okay, whatever. dn0 dE e minus mu of ex dx. But remember that our detector can only count quanta. Okay. So what we are actually doing is that no matter what the energy is, at the end, if we don't have spectral resolution, then we are counting the integral of this quantity, so the number of photons, which is the integral of the spectrum. Okay, so why are we doing this? Because if we look at how images are reconstructed in tomography, so if you take images at different angles, and then from this set you want to build a three-dimensional image of the full object, okay, then what you can do, if we work in this approximation, so there is no energy dependence, our beam is monochromatic, okay, then we can do a very simple operation. So we take this equation and we just do mu x dx equal minus logarithm of n over x and 0. Okay, which is, it's very simple. I mean, I just inverted the exponent. So yeah, and why is it important? Because it can be proved that this equation is actually analytically solvable. So if your image is this one, or your set of images is this one, so this is going to be the full set of your images at different angles. Your unknown, the one that you want to know, is this one. This is the real object that you want to reconstruct. Is the density or the attenuation inside the object, which tells you what material this thing is made of. Okay, then this equation is invertible, and you can find a solution mu x y, because we are in 3D maybe, x, y, z, which is some function of the nx, whatever this is going to be. Okay, this analytical solution is known as FBP, filtered back projection. Okay, which is yeah, is the very famous analytical solution of this problem, which is the radon transform problem. Okay. Okay. On top of the analytical solution, okay, you can also go for non-analytical solutions. You can derive iterative methods, algebraic methods, solving system of equations, but all of them work if you are in this setting. Okay, if you can write the radon transform of your image. And this is only possible if you start from here. So where there is no dependency on the attenuation coefficient. If instead you have to start from here, you see that you cannot do the inversion of the exponent with the logarithm. Okay, so all these methods, FBP certainly not, it will not work, and possibly also other methods which are derived using this assumption will not work. Okay. So why is this important? Because despite people know that these methods are would be approximate if you use them on data which have been taken with polychromatic sources, okay? People use them because they're very fast, they are very reliable. You can adjust them in post-processing, so you know that they're going to fail somehow, but you know how they're going to fail, so you do some adjustments, and somehow you can actually reconstruct something which is close to truth. But there are some cases in which they fail, you know, in a beautiful way, which is, for example, this. These are two examples of two CT reconstructions of a skull, and you see it here very well. Okay, you see this man or woman had an implant, a metal implant here, and metal is absorbing X-rays much more than all the other tissues of the patient, which means that it's going to cast a shadow of X-rays behind it. So the X-rays are disappearing inside the metal, and there are none left to image this part. These are under shadow. In the reconstruction, if you don't take this into account, so if you're not considering how this effect depends on energy, you would get this kind of artifacts if you do a reconstruction using these methods. And similarly here, where you see that there appears a shadow here in the brain, which doesn't mean that this person is missing a piece of brain. It means that all the bone which is around here is going to cast a shadow on the stuff that has to be imaged here. So there are not enough photons here to image the brain. But the algorithm doesn't know it, because this effect is very energy dependent, and this is not included in the reconstruction algorithm, at least not the way it is derived for reconstructing these images. Okay, then one thing we can do is that if we want to include this in the reconstruction, okay, we have to consider how different materials behave at different energies in the realm of X-rays. So if you look at the absorption coefficient, or something that can be related to it, as a function of energy, you see, okay, it goes down with a power law or something more more structured, but it is clearly different for different materials. Okay, and even different materials show characteristic lines which correspond to the K edges and all possible electronic transitions. But okay, these are let's say let's not linger on that. And in this example, okay, you don't see medical materials like fat bones and stuff like that. It's easier to do something to do let's say a quick test on something that we can visualize much in an easier way. Just as an example. So here this is aluminum, iodine, and gold. Some almost randomly picked materials. But you clearly see what the idea is. The energy dependency is different, and you can actually exploit this. How can you exploit this? So imagine to do a simple two-dimensional image of an object. Okay, in this case, whatever, an operational amplifier or whatever it's going to be. And you do it in different energy ranges. For example, you take your pixel detector, the ones we have been talking about earlier, and you set the threshold at different levels. So in the first case, the threshold is quite low, it's 5 keV, so it means that you detect all the photons that come to your detector which have energies above 5 keV. Now 5 keV is quite soft, and in fact you have contrast to distinguish, you have enough contrast to distinguish the soft materials inside this object, so the plastic. When you increase the threshold, now you're only looking at photons that are above 10 keV, which means that all the information about the soft materials, which is carried by the lower energy photons, now it's not present anymore. So you only have contrast in the dense materials, so the metal here. And if you move to higher threshold, you can start even distinguishing different metals. Okay. So this is the idea. If you have a detector which has the capability of imaging the same object under different energy regimes, and this could be already as simple as changing the threshold, as taking the same CT scan 3 times at 3 different thresholds. Now you have information that you can use to resolve those problems that we just saw, okay, which are very energy dependent. The trick is that you have to teach this to the algorithm. Okay, if you do something very coarse, you just do 3 CT scans at 3 different thresholds, and then you look at correlations between the values of the reconstructions. Then you clearly see that 3 different materials can be actually very well separated, as you can see in the correlation plot on your right. And you get and you get an image which is which actually I forgot. I don't know where it went. Well, it's the one I have here. Okay, this one. Okay, it's an image of this object in 3 different materials. Okay. But here you just looked at how the values of the reconstructed images at different thresholds have correlated according to that plot on the right. Okay, if you, I will not, let's say, okay, there is a lot of stuff that we are not really interested. If you do this properly, you are going to include this information in the image reconstruction algorithm, and this you can do it, let's say, I don't say easily, but if you already start from a formula of this type, and then you include the fact that your detector now is measuring not over all the energy range, but from a threshold up to, infinity. And then one thing you can do, for example, is a statistical approach. Okay, you say that this is the number of photons that you see, which is obviously a statistical quantity, something that fluctuates according to a Poisson distribution on first approximation list. So you can say that you actually have a P of n, which is something Poissonian, okay? So it's a Poisson of n given a mean value n. And you can build a likelihood function of this, and you can minimize or maximize the likelihood in order to solve your problems. This is quite tricky. I mean, it's not something I want to cover here, but you can definitely do something like this to solve your problem. And this is a very simple toy Monte Carlo exercise that I did. So you see, you start from an object which is like this. It's quite random indeed, nothing very special. I simulated an X-ray CT scan at 3 different thresholds, and then I reconstructed this object using this, this maximum likelihood principle. And the image that you get as an output is not a scalar image anymore. It's an image which is decomposed into the materials. And in fact, you get a vector of images. Okay, and in this case, you see that we get a vector of images, each component of which is is the image of a single material. Okay, now I cannot do, I mean, it's not really worth going to the details of this, but the idea, the idea is this one. Once you have a detector which allows you to achieve a spectral information on the data you are measuring, you can do something to actually improve the image capability of the system. And a few years ago there was the first announcement that one of these algorithms was actually used to reconstruct a human, let's say, a human image, let's say, and this was the wrist of the guy that actually did this. And just in the last few days, I also bumped into results that were presented by people who actually devised reconstruction algorithms based on artificial intelligence, and they're achieving quite good results. So they tested this on this sample made of water, and water in which they dissolved different concentrations of either gadolinium or iodine. And you can see that when they do the scan and they reconstruct the images, you compare FBB, filter back projection, so the standard algorithm if you want. If you go into the material decomposition, they see that there is really not much to distinguish between the various materials. But if you start using artificial intelligence based algorithms, you see that there is quite some clear distinction. Okay, these would be the what is it? Yeah, I cannot read. Okay, it's either the iodine or gadolinium, and this is the other one. So you can really see the differences. Okay. Okay, so that was one of the examples I wanted to bring. The other one would be something which I find quite fascinating. It's the fact that these detectors, okay, these are their spectral capabilities. They can measure energy, but let's not forget that they are pixel detectors. So their main goal is to measure, spatial patterns. Okay, so images, and we can actually use them to image radiation itself. Okay, so if you take this as an example, this was a pixel detector that I was doing an experiment here. I was at a beam of I don't remember what, some hadrons, some pions probably, and and I was measuring, I was tracking these hadrons. Okay, nothing special, but every now and then you would see events like this. Okay, and these events are basically pions or whatever those hadrons were that interact with some atoms of silicon or whatever they find there, and they break it, and you see the fragments just traveling in silicon and being detected by the pixels around. And the color scale actually tells you the energy. So in fact, you could even recognize the Bragg peak here. So for example, here you have whatever this is going to be, an ion that travels a distance, and you see that the energy, which is encoded by the color, is increasing as the ion travels, and most of the energy is lost at the end, which is the typical pattern of the Bragg peak. Okay, it's a very nice way you can actually visualize radiation on a single detector and all the possible interactions that there can be there. So someone has compared these detectors to bubble chambers, calling them digital bubble chambers. In fact, consider that the resolution is the one of the pixel, and the pixel size here is 55 microns, for example. So it's quite a fine detail of the interaction. And you can do something even more fancy. We know that different particles have very different behaviors. So you can do this to distinguish particles according to the geometrical pattern they leave in the detector. So you expect these things to be ions, these very long trails to be muons, single spots are going to be photons because they just do photoelectric effect and then they disappear in a single pixel. Larger blobs are going to be alphas. So you can do this to actually do a lot of interesting research with this. And in fact, a very interesting project was this one. One of these detectors, or maybe more, a bunch of these detectors were shipped to the International Space Station, and people were doing exactly this. And based on the position where the station was, they managed to reconstruct the flux of cosmic radiation and to separate it into different species just by looking at the pattern on the detector. Okay, it's quite fascinating. Okay, and then maybe probably the last thing, it's really, as I told you, it's a list of examples basically. This is an experiment in which I took part, which is the measurement of transition radiation. Now, transition radiation, if I don't know, it's not something that is probably not very familiar. It's not very common outside high energy physics. I don't really know, but it's the radiation which is produced by a charged particle which crosses the boundary region between two mediums of different refractive index. So when the particle crosses this interface, it has to readjust its velocity, basically. Well, it doesn't, but because of this, there is some leftover energy, let's say like this, which is emitted in the form of electromagnetic radiation. And if the particle is ultra-relativistic, this radiation is actually in the X-rays, so it can emit X-rays when crossing this boundary. And this effect is well known since the 40s. It has been calculated, and people have calculated the theoretical spectra and the distribution both of energies and angles. And okay, and we have been using this to build detectors, of course, but okay, let's not go into this. And the nice thing is that it has quite some interesting properties. So first of all is that it's if you look at the angular distribution, it turns out that it's proportional to 1 over the gamma factor, the relativistic factor, which means that if the particle is very relativistic, the radiation is very forward. The only problem is that it's the chance of it being produced, so the chance of producing an X-ray when crossing this boundary goes with the fine structure constant. So it's 1 over 137, so it's very small. So what people do typically is that they build something, I don't have a picture, but they basically build an object which is called a radiator, which is basically an array of many of these many layers of something, and so it's basically an array of alternating refracting index between this material, which is usually some plastic, and air. So you actually increase the chance of this being produced. So in this experiment, what we did is that we went to a mixed beam of pions and electrons, okay, and we realized this setup. We have a radiator, which is the thing you see here. So this is the object that enhances the production of X-rays. Then the X-rays that are produced here, since they are very forward, because this is a very high relativistic beam, they would travel into this helium pipe, so they will not interact that much. I mean, the chance that they make it to the other side is quite high. And at the other side, we have what we call a telescope, a silicon pixel detector telescope, which looks like this. And the idea is that the central particle, so the hadron or the electron that has produced the transition radiation, will be detected somewhere here in the center. And then the photons will arrive with a certain angular aperture. And if the setup is made in a good way, then the distance between the two is larger than the pixel size, and therefore you can actually distinguish the photons from the central particle, from the charged particle. Okay. And the point is that transition radiation is something that I told you, it's known since the 40s. We have been using it in our experiment quite extensively, but before this one, there has never been a measurement with so much level of detail as I'm going to show you, that shows the energy and angular distribution of this radiation. Okay, okay, so we receive events like this, as you can see. So a central particle, which is detected like this, and either nothing or a separated photon. Okay, so we do some event selection and some more refined analysis, and we start seeing something which is basically quantum mechanics, because it's basically this transition radiation and all the fringes that are foreseen by if you do all the calculations. And okay, and at the end, with some more analysis and exploiting the fact that these detectors not only allow you to measure the angular distribution, but they also give you for each photon the energy. Okay, combining all of these, we get to this final result, which is this is the first ever measurement of the differential spectrum in both energy and angle with this level of refinement, let's say, where you clearly see all the fine detailed pattern which is foreseen by the theory. Okay. Okay, and then comparison with Monte Carlo is very good, and not much more, let's say. Okay, and then this is just a few examples of what else people have been putting on top of these detectors. If you remember, I said at the beginning, if you work with a hybrid concept, you can also, you can choose the sensitive part as you want. It's not necessary that you put silicon or a semiconductor on top. In fact, what these people did in Amsterdam, they took one of these pixel electronics and they built these tiny micro pillars on top of which they laid a metallic mesh, and then by applying a potential difference between the mesh and the input electrodes, they actually achieved amplification by avalanching gas. And by exploiting the time of arrival measurement of the pixel electronics, they could measure the time it takes for electrons to drift in this gas, which is proportional to the height, to the distance to the point at which they were generated. And in fact, this is actually working as a tiny, because the size is this one, time projection chamber. So a gas chamber that reconstructs tracks in 3D. You see it here. These are tracks of 2 electrons reconstructed in this thing, which is just 1 centimeter cube in a magnetic field. Or people have been using this concept of time of arrival to measure the time of flight in a mass spectrometer. And this is what you see here. They basically they took a commercial time of flight spectrometer and replaced the detector that was there with one of these pixel detectors. Unfortunately, it cannot really be seen, but the improvement was from this image here, which shows, well, very broad peaks, to a huge number of fine detailed peaks. Just because the time resolution of this detector is in the order of, a few nanoseconds. Okay. Okay, so that was just, a list of examples. As I told you, it's really the tip of an iceberg, which is growing and growing every day. And but I think that this kind of technology is really has a huge potential. I'm currently working on basically the same technology for high energy physics, but I always keep an eye on what's going on outside of this field, because I really think that people are doing very, very beautiful things. So again, many thanks, and thanks for your invitation.